let's do a couple examples. So the first one says dy dx equals sine x squared. So the slope, so let's think about some points. You got to kind of flip over to look, but here's what I do. I think about some 25. I think about some points on the graph. So I think about like at 1, 1. At 1, 1, what would the slope be? Well, the slope, remember, is your derivative. So I plug it in, and I'm only using the x because that's all the differential equation gives me. So what is, okay, this was a terrible one. Let's do 0, 0. And then because I'm going to assume these windows are trig windows, so they're going to be by half pi's. All right, so at 0, 0, I've got the sine of, what's the sine of 0? 0. What does a 0 slope look like? Horizontal, right? So if I'm looking at these equations, that automatically knocks out A, or these graphs, I'm sorry, that automatically knocks out A and D. So I'm between C and B. Y'all see that? Do you agree with that? Because those are the only two that have, actually not even C. Because at 0, 0, C doesn't have anything. Do you see that? So it'd have to be B. Does that make sense? Pick a point, and preferably something that looks like it's a little different than all the others. Yeah. Hmm. I wonder if that's supposed to be down on 0. What is the graph of? This is, I'm sure, a non-calculator problem. Give me just a minute. Let me show you these two because they're very interesting. Let me just make sure. I'm fixing to show you this for a reason. Look at these graphs. I'm going to do sine x cubed first. I want you to look at it. That's interesting, right? Now watch what happens when I do sine x squared. And I'm going to graph this a little bit bolder so you see it. It just took all the negatives and reflected it up, so it's pretty much the same. Doesn't help you with the slope field on that, but I thought that was cool. All right, so let's look at the slope field. Why is the slope field? Let's put this. Why is it C? I see what you're saying. That's because just like with that graph, the sine x cubed could go below the x-axis, but sine squared couldn't. It flipped everything up. But is everything else the same besides that? It's not. Looking. Pi over 2, 1. Well, this one's hard. I am going to say on this one. Read me what it says again. Yeah. What's their explanation? Because this is not a graph you would just really know. Okay. So they're putting. They're looking at whenever it flips, because whenever you get a negative value, if you're squaring it, it's going to stay positive. If you're. That's why. Look at B. And look at all the slopes on B. What do you notice about the slope? It's always what? Positive, because the function's always increasing. Part C has some that are negative. See, as I come here, I'm starting to get negative. It still does not answer your initial question that you were asking, because at 0, it should still be 0. I can't answer that because I feel like this should be down here at 0. And then I could understand it a little bit better. So, right. I understand the slope thing, because if you're raising something to a third power, then you can have a negative slope. But if you're squaring it, it's always positive. So these would be your 2 squared functions. These would be your 2 cubed functions. But I agree. I think it should be shifted down some. I've not seen anything like that. I have seen ones like that, but I've not seen the trig functions like that on any type of exam. All right, well, what else? That was a bust. Give me one I can do. Do what? 39 and 30. Oh, the ones I just showed you. All right, so 39 is. Yeah, have to do 39. That's okay. All right, so I'm matching that to one of the graphs. And again, and as I look at this one, my first clue here is I know that x can't be 0 on the bottom, right? I'd be undefined. You agree with that? Well, I don't see any of them having an x value of 0. I'm just kind of looking. What do the blue dots on here mean? Do y'all have a blue dot on y'all? Oh, it's like an initial value thing. I gotcha. All right, so I guess let's pick some points. Let's look at it. You could actually reason through this if you wanted to. I guess I should have left this plugged up. So start picking some points. I generally just pick random points until I find the one that has all that. Like I might say, okay, at 1, 1, what's the slope? The slope is -1. So looking at these graphs, which one has so they all pretty much look like they're going to have, well, I can eliminate E. I can eliminate C. Maybe can eliminate A. I'm going to leave it for right now. So right now I've knocked out C and E. So let's pick another point and let's look at where things start doing something different. Where things start. Notice here as my y stays the same. So let's assume like y is 1. As x gets bigger, what are these values getting closer and closer to? 0. As x gets bigger and bigger and bigger. So maybe it's easier to look at this and match the graph. But that's what clues me in on this one. They're getting closer and closer to being horizontal. So as I put bigger and bigger numbers in for my x, but I keep y the same, let's say y was 1, and I get really big down here, this is going to 0. I don't see any others that are really doing that as I go across. It looks like A is definitely not, so that wouldn't work. D is getting more vertical, so it's getting closer and closer to being undefined. And F isn't changing a whole lot as I go out. So I'm going to go with B. And then it says, then what else do I have to do? Match the appropriate, then use the slope field to sketch the graph through the highlighted point. So what do you think about the graph? Any ideas? Yes, no, maybe so. Can you see the graph in it? How could I maybe find an equation for the graph? How? Find the antiderivative. I have a y in there though. Is that going to impact? That might impact me a bit. Follow the slope lines. You're looking like you're. If this is going here, I'm looking like this is a reciprocal kind of function. I'm thinking it's going like this with some asymptotes here. The graph itself kind of gives you the picture that's going on. Does that make sense? I feel like no. Mhm. It does look like a circle. If I do antiderivative there, which I'll have it on. This is not going well this morning. Mondays never go well for me in here. I don't know if y'all have noticed that. It is. It is. It would be. That's okay. Yeah. And it just follows through. And if you look, I mean, all of these kind of, the sketch of them is just almost following these slope lines through as you go. Here, if you know this is a point, I'm doing something kind of like this. Here. Does that make sense? I'm just kind of following the slope along. It's just a sketch. It doesn't have to be exact because we're going to talk about how to do it exact soon. Does that make sense? Are you sure? I don't believe y'all. You say no? Okay, so 35 is dy dx equals x, right? So whatever your x value, that's your slope. Doesn't matter what y is. So what should happen is at every x, up and down, right? Because x stays the same. So if x is 1, then up this whole line, every slope should be the same. If x is 2, then up this whole line, every slope should be the same. Because as long as x is not changing, the slope is not changing, right? Does that make sense? So this one, clearly they're changing as I go vertical. As I go vertical here, they're still changing. Here, okay, now I might have one here. They're all the same. They're all the same. They're all the same. They're all the same. See what's happening? The slope is equal to whatever that x value is there. And it's not, I say it's equal to x, but it's the same thing up and down. And if I look, if x is 1 here, that looks like about a 1 slope, right? Here, x is bigger. Is the slope getting steeper? Yes. And steeper and steeper and steeper still. Does that make sense? And it makes sense if you look, the equation up here was dy dx equals x. Well, if your slope is x, what's your antiderivative? What's the antiderivative of x? 1/2 x squared, which is just a what? A quadratic. It's a parabola. And look, you can see the parabola there. Same thing with 36. 36 is dy dx equals y. So I'm looking as I go across, are all the slopes consistently the same if the y value is the same? No, 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 no. Well, whenever I get to E, it looks like they are as I go across. We'll practice some more with some slope fields. I'll give you some slope field practice. And I got a program for your calculator too. How about 41 through 46? Did y'all struggle with those? Yes. Okay. Look at 41 first. Dy dx equals the square root of x squared minus x plus 1. How about at 0, 0? What's my slope look like? 1. How about at I wouldn't be undefined anywhere here because I'm squaring. That's going to be bigger than subtracting the x. How about at, let's pick one in the first quadrant. How about at 2, 0? So I'm still positive. But what do you notice doesn't exist in my differential equation? There's no what there. What variable's missing? Y. So what does that mean in terms of my slope? That's exactly right. Y is not impacting my slope at all. It doesn't matter what Y is. As X changes, that's the only time the slope is changing. So as I look at these pictures, it's the same kind of scenario. Up and down, the slopes are the same. It doesn't matter because as long as X is the same value, well, here they look like they're changing, right? Not a whole lot, but they're still changing nonetheless. Here, are they changing? They look the same there. They look the same there. B might be a good option, but let's keep looking. C definitely couldn't because they're differing as I go down. How about D? D looks the same up and down all the time. How about E? E, nope. F, nope. So it's got to be either B or D. So what's the difference in B and D here? What's different? What'd you say? The Y? Oh, yeah, the slope. It's got to be D. It's got to be D because when X is 0, we already figured that out. When X is 0, what's the slope? 1, right? This has got a slope of 1. This has got a slope of 0. So it's got to be D. Does that make sense? I'm not sure that I believe y'all. Do we need to practice with slope field today instead of moving on? We're going to use substitution today. It's a little tough. But if y'all need more practice with this, how about the differential equations when you were solving the initial value problems? Hard, easy. The differential equations where you had to solve the initial value, the C, find the C. Those are easy. It's just the slope fields. Yeah. Indefinite integrals this time. We've been working with definite integrals, which means what? Hope you look so excited. It means definite. A definite integral has bounds to it. It has this A and this B, right? It tells you these values. An indefinite there are no bounds, okay? Indefinites give us the plus C on the end because we don't have those values to plug in when we find the antiderivative. Now, all the same properties, all the same rules still apply as far as you can add, you can subtract, you can pull that constant out front, all that's the same, whether it's a definite integral or an indefinite integral. So just as a reminder, if I'm asked to evaluate that, what would that equal? Y'all can do this. What's the antiderivative of x squared? 1/3 x cubed, right? Are y'all following me? What's the antiderivative of negative sine? Or actually, we'll say, okay, what's the antiderivative of sine x? I can split it up because I'm adding or subtracting. Negative cosine x, right? Remember, because I'm going backwards here. So negative cosine x. And I have to follow with this plus c because it's an indefinite integral. Because it was subtracting here. So this is like this. Now y'all are really gonna hate me. Okay. Yeah. Yeah. Because since I was subtracting, I could split that integral up to find those values. Remember, as long as you're adding or subtracting, not multiplying or dividing, you can split the integral that way. Everybody else okay? Yeah, sure. If it's really not bad. Okay, so we evaluated an exact value before. Now we're saying if I don't want, now I just want a general equation for the integral. Before we found the area under the curve, yada, 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 because we had two values to go between, right? And we said, oh, here's your curve, whatever it may be, find the area from here to here. Now we're just finding an equation for the antiderivative, essentially, is what we're doing. Instead of worrying about area, now we're just worried about an equation for the antiderivative. Okay. This is where all your integral rules on the back of your paper come into play. Back of your derivative paper. If I change it to a u, it still has the same function as x, right? Here's the part where it's going to get sticky, though. We're going to start putting things in place of this u, whole functions in place of this u, and making sure we have this du on the inside so that we can integrate. So let me just jump straight in and show you exactly what I'm talking about. Let me find a good one. For example, this looks rather scary. You agree? I can't split integrals up that are being multiplied, so I couldn't just say, well, I'll just split this up. So what I do is I look for a function within the function whose derivative is also included in there. Okay. All right. As I look at this one, I'm thinking, I told y'all, just stay with me because they'll start to pop out at you after you understand what exactly it is we're doing, okay? As I look at this one, the first thing I notice are that sine and cosine are derivatives of each other. Do you agree? Yeah? Okay, so what if I said, well, I might not can take the derivative of this, but what if I let some variable be cosine x? I call that variable u. What is the derivative, or what would du be? And I have to follow with the dx, right? Because I'm taking the derivative with respect to another variable. Okay. So now could I rewrite this using my u's? Look at what I have. If I just move this around a little bit, I'm very, very close to having negative sine x. In fact, I have e to the u, right, times, well, sine x times dx, what I really have is negative du. Du is negative sine x, and I have sine x dx. It's just missing a negative, right? Do you agree with that? So I'm kind of rewriting it. So this negative here, to kind of counter that, because it's gotta have the same value. I can't just throw a negative in there willy-nilly because I want to, right? But I could put it out here also and say, well, the two negatives together make a positive, so they really go away. I forced this to be e to the u du. Why did I do that? Well, I did that because I know the antiderivative of e to the u. I didn't know the antiderivative of sine x e to the cosine x dx. But I do know the derivative of e to the u du, right? Or antiderivative, excuse me. What is the antiderivative of e to the u du? I got a negative out here, right? E to the u plus c. Well, now I can go back and go, well, wait, what was u? Cosine. So I've got negative e to the cosine x plus c. And that negative out front, not going to that c, doesn't matter because c is an arbitrary constant. It could be positive or negative. That doesn't matter. Now I have found the derivative, the antiderivative, excuse me, of this indefinite integral. I know it is a lot when you first look at it and you go, holy crap, I'm never going to be able to do that. I'm never going to be able to see the u, but you will. Okay, so this, I kind of thought about it like this. This is the same thing. I'm just going to write it a little bit different. I'm going to write it here. Times sine x dx. Agreed? Same thing, I just moved the multiplication around. Well, u is cosine x, and du is all of this, but it needed a negative. So if I give it a negative, it would match. But I can't just put a negative in there because I want to, so I have to counter it with a negative out here. And together those would cancel out. That's the hard part, is figuring out what u and du have to be. So that's why I said you're looking for a function that you know the derivative of, and you know that that derivative is also included. Because what I'm going to have to do is I'm going to have to find the derivative of the u. But I'm trying to get rid of so many functions in there so that I can evaluate. Let's do another one. If I'm asked to find the antiderivative here, I'm probably just going to cry right now. I'm not going to cry because I know how to use substitution. But if you look at it, it's quite intimidating, right? You're going, holy crap, antiderivative of that, what in the world? Okay, so is there something in there that you could take the derivative of, and once you take the derivative of that, the only thing that's left in that integral is that derivative? Am I making sense? No. Okay. Do you see a function in that integral that if you were to take the derivative of the entire function, that derivative is, gosh, I can't say it. I keep just saying the same thing. Okay, let me say it one more time. Maybe it'll make more sense. What I see here, the first thing that I noticed in here was I've got this 2x cubed, right? And I know that the antiderivative, or I know that the derivative of anything to the third power is something to the what power? Second power. And I see something that has a second power here. Do you see that? So I'm kind of looking for something with the power below. Good morning. Their brains, they're going. How are you? All right. Any ideas on what I could let you be? 2x cubed, and maybe even bigger than that. Because remember, when I take the derivative of constant, that's 0. So I'm thinking, what if I let u be? Because remember, whenever I plug it in, I want to be able to take the derivative of u, and whenever I do, the derivative of u is the only thing that's left in there other than what I substitute. So let me show you what I'm talking about. Yes, you have to determine what u is. You decide which needs to be u. It wouldn't make, if I let u be x squared, well then du would be 2x dx, and that doesn't do me any good in this problem, right? So then I'd go, wait, that doesn't work. Well, what if I let u be 5 plus 2x cubed? Then what would du be? It's going to be, yeah, it'll probably, yeah. Well, but over here it's not u's not e to the cosine x. It's just the cosine x that's up top. You see what I'm saying? So it kind of depends. Sometimes it won't be a whole half of it or a whole piece of it. All right. So what's du here? 6x squared dx. Okay. So don't once you pick your u, take the plain old derivative of it. I know you start getting so mixed up on antiderivative, derivative. What am I doing? Okay, is this in here? No, but very close, right? The x squared's in there. So if all you're lacking is something that's being multiplied, I can make that happen. Y'all see it dividing. Some people see it that way. I have to see it. This is how I have to see it. I have, like, y'all are doing this, right? So du over 6. The way I, which is fine. A lot of people see it like that. The way I see it is I have to go, okay, this would be the square root of u. I need a 6, but then du is there. How do I counter this? Well, I counter this with a 1/6 outside. What? What? I don't understand what y'all are asking. Okay, this is just saying I need to make sure this is what's left inside here. Well, the way it sits right now, I've got square root 5 plus 2x cubed times x squared dx. I'm missing the 6. So I would need a 6 to be right here in order to make this be du. Oh, you're saying this. Yes. Yes. Sorry. Yes. Yes. Sorry. I need the 6 here and I need to counter it here. Yes. You're right. I'm sorry. So you do have to put the counter part of it on the outside. Okay, so then this is 1/6. Well, why did I do this? I did this because I can easily find the antiderivative of the square root of u. Because remember, the square root of u is just u to the 1/2. What's the antiderivative of u to the 1/2? So add 1, right? And then divide by that in front. So 3/2 is my exponent. What's the number in front? 2 over 3 in front, and I've still got this 1 over 6 out here, and don't forget the plus c. So the du, remember, whenever I take the integral of anything, if I do x dx, then this just says take the integral with respect to x. So it just becomes 1/2 x squared plus c. Okay, so now I can kind of put this together. This would be 2 over 18, which is 1/9 u to the 3/2. But remember, I put the u in there so that I could evaluate this whole integral. What was my u? 5 plus 2x cubed. And I just fill in the blank. Y'all clearly. Yes. Some people do, and I don't know what. Yeah, look it up as I challenge you a bit more. Integration. Russell does something at his job was with integration. I don't know what it is. I'll have to ask. He has a spreadsheet calculates it for him though. Chemist. Your book eases you into this a little bit more than what I probably have, and that they give you the U in some of them. They give you the U in this one, but this is an easy one to find the U. So tell me what you think the U would be here. Look at you go, Adam. Now help me explain why you chose that. Not always, no. But a lot of times, yes. A lot of times, yes. What would DU be? 7DX. I don't. So here's how my brain works with this. My brain goes, I don't want that 28. It's interfering with what I'm doing. I'm just going to rewrite this as 28 times the integral of 7x minus 2 cubed dx. Now, if you don't do it this way, if you think through, some people solve this for dx. I think that's what y'all were doing before, and then you plug in. It doesn't matter. This is just how I think about it because I'm very, I don't know. So, right, that's exactly what you would do. So here, I need this to have a 7, and to counter that, I need to divide by 7. So now I have 4 times the integral of u to the third du. A 3? You mean 4? No, a 7. A 3. Because du, if I make this u to the third, I need this to be du. To make that be du, it's missing a 7. Because du is 7 dx. Yes, yeah, and then I'm countering it on the outside. Yeah. You can't divide by 4. Why do you want to divide by 4? Why do you want the 28 to be 7? Because that's my du? Okay, yes, but if you divide this by 4, you would have to counter this with a 4 outside. Yes, you can do that. That's the other way to do it. It's harder for me to see that, but if that's how you see it, that's fine. Yes. If you come up with your du and you see what it is and you understand how to manipulate it from there, that's fine too. Now can you do the antiderivative? Yes. Yes, we can. What's the antiderivative of u to the third? 1/4 u to the fourth. Don't forget the plus c. What was my u? If you want to check your work to see if you got it right, you could always take the derivative here. 4 times 7x minus 2 to the third, and then you got to chain it times 7. And that's what you started with, so you did it right. What do you think? It's worse than it looks, though. I mean, it's not as bad as, oh my gosh. It's worse than it looks, guys. This is 20, yeah. Not 24. They give you the U on these, but I'm making you think a little bit harder and making you come up with the U. If I mean, you're welcome. Glad I could help. Remember, when you take the derivative of what you let be U, it has to be whatever else is left in there. So if I took the derivative of this, I'd get 3y squared plus 2. That's not in there. But if I take the derivative, yes. There you go. That's right. If I took a 4 out of here, I'd be left with 4y cubed plus 2y. And look at that. It needs only what? A 4. And this 8, yes, just divide. This 8, because again, I do things weirdly. If you divide it by 4 in the beginning because you see that, I think that's what Alex is doing. I put it here and I divide out here. So I end up with 2 times the integral of u squared du. Well, now that's a lot easier to do. What? Because my du had a 4 in it out here, so I had to add that 4 in here to make all of this du. Because if I multiplied in here, I had to divide out here, and I moved that 8 outside. Now, if you see it like they see it, where they went, okay, well, divide both sides by 4 here, so you divide it. You can do that too, either way. 2/3 u cubed plus c, and then just plug that u back in. We will practice with this tomorrow and possibly the next day as well, because I multiplied. It's because it's 2/3. Yeah, 1/3. That 2 was out here, so I did 2 times 1/3 u to the third. Antiderivative of u to the second. Add 1 to the exponent and divide. I know. We'll go easy tonight. Nope. Nope. Don't you have to what? Yes. So this would be 2/3 y to the fourth plus 4y squared plus 1 to the third plus c. 24. This is the last one. Shoot a monkey. Is that what you say all the time? Yeah. Yeah. Shoot a monkey. Anybody got you? 10. I so appreciate your enthusiasm. Anybody else got you? I love you, Grant. Anybody? I would say theta plus pi over 2. What if I let you be theta plus pi over 2? Why might I do that? But doesn't this look familiar? It's the derivative of something, right? Of secant, right? Whenever I saw this one, I went, wait, that's the derivative of something. There's something that's the derivative of. And if you look on your sheet, that's why I threw it up there. That is just a variable like x. Because it's 1. Think about it. If it was like x plus pi over 2, it would just be 1 x. You just follow it with whatever yeah, theta's a variable. Yeah. The derivative of secant x is secant x tangent x. She just said, where did the tangent go? All right, let me give you some practice. Let's see what we're going to do. It's not. All right, let's do. All right, these do not have U sub in them, and they're not hard, but just getting you back into some of those. Just integrating with the plus c, just definite integrals. Like the integral of x to the negative 2 dx. All right, these give you the u to use. And then I'm going to hand pick a couple for you to do that don't give you the u. Let's do 25, 26, and 27. Bless you. because we did 28. I'll stop there. We'll pick back up tomorrow.